Welcome back to the Steam Locomotive Valve and Valve Gear tutorial series. I'm Dan Oberklein, and in this video, we'll show how to build a valve gear mechanism that provides the proper valve motion for a steam locomotive to run. We'll cover step-by-step development of a mechanism that drives the valve with a motion that satisfies the requirements for a properly running engine. Geometric features of the running gear that need to be addressed or compensated for in the valve gear arrangement, and nature of the valve motion and how it changes as the cutoff setting is changed. In the last video, we developed the 3 rules of valve motion, and they will be our guide as we construct the valve gear. The end result will be the Walschaerts valve gear, which was the most widely used valve gear on locomotives from the early 20th century to the end of steam. In a later video, we'll look at Baker valve gear and see how it uses a different arrangement of levers to produce a similar valve motion. And once again, we'll use C&O's superb Class K4 Kanawha type as our example. Now, something looks a little strange about this locomotive, and that is because the K4, like all the Van Swearingen Berkshires, had Baker valve gear, not Walschaerts. So if you ever wondered what a Van Swearingen Berkshire would have looked like with Walschaerts valve gear, here it is. This is actually not that far-fetched because valve gear is typically mounted onto a beam that is part of the locomotive frame casting, and valve gear frames typically have one of several more or less standard designs, making it possible to remove one valve gear unit and mount another on the locomotive. There is actually some precedent for this on the C&O, where the first order of Greenbrier locomotives were delivered with Walschaerts valve gear and later converted to Baker. We'll zoom in on the running gear, and this view shows all the engine drivetrain components, from piston and valve to rod and wheel. Once again, let's cut away the cylinder casting so we can see the piston and the valve inside. First, let's remove all the valve gear components and build it up one step at a time. This way, we can see what components are needed to achieve a motion that satisfies each of the 3 rules. With all the valve gear components removed, we are left with just the bare bones of the drivetrain, the piston connected through the crosshead to the main rod, and side rods connecting all the drive wheels. This is not even an engine at this point. It will not run if we supply steam to it because there is nothing to move the valve in time with the piston or the wheel's position. So valve gear is not just a nice-to-have performance enhancement. It is an essential part of a working steam engine. We will start from this basic drivetrain and build up a working valve gear. The valve stem has a crosshead that rides in a crosshead guide to hold its motion in a straight line, just like the main piston crosshead. Valve crossheads and guides can take several different forms. This one consists of a U-shaped bracket that slides back and forth in a channel formed from beams bolted together on each side. At this point, let's review valve motion rule number 1, which requires that the valve's motion is about a half stroke behind the piston. To satisfy this rule, let's start by looking at the relationship between circular motion of points on the wheel and reciprocating motion of things like pistons and valves that are mechanically connected to the wheel. Starting at the main crank pin, let's project its motion onto a horizontal line which runs parallel to the direction in which the piston moves, and watch the horizontal component of motion as the wheel rotates. We see that this horizontal projection of the crank pin's motion mirrors the piston's movement. The crank pin is furthest back when the piston is at back dead center. Then it moves furthest forward when the piston is at front dead center. And here the crank pin and the piston are both in the middle of their travel. At this point, we need to digress for a moment and observe one geometric quirk of the motion here. In this view, the crank pin is exactly midway around its arc of travel from front to back. But if we look carefully, we see that the piston is slightly more than halfway along its rearward stroke. This is because the main rod needs to angle slightly away from the horizontal to follow the crank pin around its circle of motion. With the rod angled like this, less of its length is available to reach in the horizontal direction back to the crosshead, so the crosshead and piston need to move a little further toward the left to make up for the main rod's lost reach and remain connected. Another way to see this is to imagine that the main rod did not need to angle off the horizontal to reach the crank pin. In this case, all of its length would always be available to reach straight forward to the crosshead, so in this view, the piston is exactly at mid-stroke. Back to reality, if we connect the main rod to the crank pin in its actual location in the first quarter position down here, notice how the piston moves slightly back in its stroke to meet the main rod's shorter reach. As the wheel continues to rotate and the crank pin moves back to the central axis, the main rod angle closes back up, and it gives back the extra distance that it borrowed from the piston during the first quarter of rotation. The effects of main rod angle and the uneven piston stroke can be minimized by using a longer main rod. Our C&O K4 here has a main rod that is 132 inches, or 11 feet long, which is a common size for large locomotives. On this locomotive, this length means that the main rod never angles more than 7.4 degrees from the horizontal, and at a quarter rotation, the piston is just a little more than 1 inch from the ideal mid-stroke position. This same phenomenon occurs in internal combustion engines, where the piston moves further during the first quarter of crankshaft rotation than during the second quarter of rotation. A longer connecting rod will make the stroke more even, just as the main rod does in a steam engine. Returning to the projection of the crank pin's motion along the horizontal axis, we have seen how this tracks, but does not exactly copy, the piston's position in its stroke. If this represents the piston's position, and it is near the center of its stroke now, then to satisfy rule number 1, we need the valve to be about a half stroke behind or at the extreme front of its travel. As we put it in motion and keep the valve a half stroke behind the piston's position, we see that the valve's motion is the horizontal projection of a point on the wheel 90 degrees behind the main crank pin. So if we drive the valve from a point on the radial line that is a quarter turn behind the main crank pin, it should impart a motion to the valve that satisfies rule number 1. We should choose a point that is closer to the wheel's center of rotation than the main crank pin, because the valve doesn't need to have as long a stroke as the piston. So let's just make a direct connection from here to the valve and see what happens. We can't just pin the rod to the wheel at that point directly, because that would interfere with the rods connected to the main crank pin as the wheel rotates. So we must tie the rod down in a plane outside the other rods, and that is how the eccentric crank is born. The job of the eccentric crank is to hold the end of the eccentric rod over one point on the main driver at all times. Now we just need to connect the right end of the rod to the valve crosshead, and we're ready to put it in motion. As the wheels rotate, we can see that the end of the eccentric rod always lies over the same exact point on the wheel, and the angle between that point and the main crank pin is always fixed at 90 degrees. At this point, our drive mechanism has become an actual engine. We've provided a means for moving the valve that will allow the engine to keep running once it has been started. It is a crude engine that will not run very well, and we need to refine it to address several major shortcomings. One problem we see is that the valve travel is way too long here. It is almost colliding with the ends of the valve chamber. Because the valve is being driven directly by the eccentric crank, the valve travel is equal to the eccentric throw, the diameter of the circular path traced by the eccentric crank. So we need to shorten the valve travel length, and there are two ways we could do this. One would be to shorten the eccentric throw by moving the eccentric rod's anchor point inward like this, closer to the wheel center. The other way is to split the eccentric rod into two segments and introduce a lever between them to gear down the motion. The lever will be pinned to a gear frame and pivot about this point. In our example here, the valve rod is hooked up to a point 1/3 of the distance along the lever's length, so the valve travel is geared down to 1/3 of the eccentric throw. So we see that as the eccentric moves the lever's length through this distance, the valve rod moves through a shorter distance in proportion to the lever arm lengths. Seeing that the valve travel is determined by the point on this lever where the valve rod is connected, we can envision a way to make the valve travel adjustable. If the lever is designed in such a way that allows the valve rod to be moved to different connection points along the lever, we can get different valve stroke lengths, and we know from the last video that this is how different cutoff settings are achieved for the engine. We'll see this in more detail later when we get to the proper Walschaerts mechanism. Using this lever action mechanism to drive the valve also suggests a way to reverse the engine. If we extend the lever to the other side of its pivot point and connect the valve up here, the valve will now move in the opposite direction when the eccentric rod pushes and pulls on the lever. This is the same motion that would result if we kept the original direct action lever drive but moved the eccentric crank diametrically across the wheel. This lever action mechanism for driving the valve appears to bring many benefits, but if we look closely at the valve position when the piston is at either end of its stroke, something is not quite right. In this view, the piston is at back dead center, and the valve should be centered, but clearly it is not. And here, the piston is at front dead center, and once again the valve is not centered, and this violates rule number 1. To stay in compliance with rule number 1, we need to correct the mechanism so the valve will be centered when the piston is at stroke end, and maintain this alignment for all valve travel settings. This condition requires that the valve remains centered when the rod is rotated up and down like this, and that is why the link must have a curved shape. The link's radius of curvature is the same as the length of the valve rod, and this is why the valve rod here is called the radius rod. The radius rod can be raised or lowered to any position along the link, and because the link is now curved in a circular arc centered on the rod's pivot point, the valve's position holds steady during these adjustments. This should also be true when the piston is at the back end of its stroke, but once again something is not quite right. The valve is not centered. This is because the curved link is not in a neutral position here, with its center of curvature coinciding with the radius rod's pivot point. Notice how the link changes position slightly when we toggle back and forth between the front dead center and the back dead center frames. And here the link is aimed slightly downward. This should not happen. The link should be centered up, with its curvature pointing directly here at the radius rod connection when the engine is on either dead center. This flaw arises because the eccentric rod joins the link foot at a point above the engine's driveline. So as the eccentric crank carries the rod's far end through its circular path, the bottom quarter point is a further reach than the top quarter point. And this further reach pulls the link foot slightly back. To fix this, we need to tweak the eccentric crank setting so that, when the engine is on the two dead centers, the crank hits two diametrically opposed points that are equidistant from the link foot. This is why, if you look carefully when a locomotive is stopped in the famous rods down position, you can see that the eccentric crank is not set at exactly 90 degrees. With this corrected crank, the link, and therefore the valve, will be in the same centered position when the engine is at either dead center. There is another flaw in the link's motion that has been corrected by shaping the link foot as shown here. We saw earlier how the main rod angle results in the piston having unequal displacements during the front and back quarters of crank rotation. This same problem also affects the eccentric rod's motion as it follows the eccentric crank around its circle of travel. And if left uncorrected, this would cause the front end of the eccentric rod to move further during the front half of the crank's circular path than during the back half of the circle. The result would be greater valve movement to the front of the valve chamber than to the rear of the chamber, and this would bring unequal cutoffs to the piston's downward and return strokes. To compensate for this asymmetry in the reciprocating motion, the link foot has been given a back set, placing it a few inches rearward of the link's center line. As the eccentric rod reciprocates and rocks the link back and forth, the angle between the eccentric rod and the link changes. At their forwardmost position, the eccentric rod is pulling on the link nearly tangentially to its arc path, perpendicular to the radius of rotation. At the midpoint of the link's movement, which occurs when the eccentric rod is in either of these two positions, depending on which dead center the engine is on, the link has rotated back so the eccentric rod is no longer pulling tangentially to the arc path. This becomes even more pronounced when the link has reached its extreme position, with the eccentric rod's rearward pull now acting nearly in line with the arc's radius. This progressive straightening of the joint here acts like a whip, snapping the end of the eccentric rod and the link foot upward. This extra motion from the straightening of the joint causes the link to rotate through a greater angle for a given movement of the eccentric rod than we got at the other end of the stroke when the rod was acting along a longer lever arm. If we move the eccentric crank and rod through the same incremental distance here, we see that it produces less rotation of the link. If the link foot were not given a back set, it would not make nearly as sharp an angle with the eccentric rod's line of action, and the extra motion from the straightening of the joint would not occur. If the link foot back set and eccentric rod are matched correctly, the link will rotate through equal arcs on each side of its neutral position, and the valve will travel equal displacements to either side of its centered position in the chamber. With these corrections, we now have a mechanism that completely satisfies rule number 1, placing the valve a half stroke behind the piston's motion. We are now ready to bring in valve motion rule number 2, which requires that the valve be displaced from its center position by the amount of the lap plus the lead when the piston is at either end of its stroke. One problem we see with the engine thus far is that we have not given any lap or lead to the valve's motion. When the piston is at back dead center, the valve is exactly centered in the valve chamber because its motion is exactly 90 degrees behind the piston. As a result, the rear port is completely covered by the valve and no steam would be admitted to the cylinder. The same thing was seen at the front port when the piston was at the front of the cylinder, needing steam to begin its stroke. We need to advance the valve a little beyond this position so the port is open to the steam chest on the admission side of the valve. Perhaps the most straightforward way to do this would be to change the angle of the eccentric crank so it is further around the wheel, less than 90 degrees from the main crank pin. When we do this, we see that it does indeed advance the valve as planned, and the valve has moved to clear the lap and open to provide the lead at the beginning of the stroke at both ends of the cylinder. Advancing the eccentric is, in fact, the method used in Stephenson valve gear to provide the lap and the lead. Before we declare this a success, however, we need to see what happens when we try to run the engine in reverse. And here we run into problems. We saw previously how shifting the lever mechanism into reverse is equivalent to moving the eccentric crank diametrically across the wheel, which means we are now effectively taking the valve motion from this point. This is not what we want because it is not closer than 90 degrees behind the main crank pin when the wheel is turning in reverse. As a result, the valve is being displaced in the wrong direction at the start of each piston stroke, effectively being given negative lead. This problem is solved in Stephenson valve gear by using two separate eccentrics located on the main axle between the frame, one set at the proper angle for forward motion and the other set at the proper angle for reverse motion. For a side-mounted valve gear like we are developing here, it would be difficult, if not impossible, to have two separate eccentric cranks both connected by rods to the gear link, so we must find a different method of providing the lap and lead to the valve. Returning to the proper eccentric crank, we can find a suggestion for another method of obtaining the lap and the lead by observing that, at each end of the piston stroke, the valve needs to be displaced in the same direction as the piston. When the piston is at back dead center, the valve needs to be displaced slightly rearward. And when the piston is at front dead center, the valve needs to be displaced slightly forward. And if we were running the engine in reverse, this same relationship still holds, because at each end of the piston stroke, we need the valve open to admit steam for the next stroke, and open means toward the end of the chamber. In all cases, forward or reverse, when the piston is at front dead center, the valve needs to be displaced slightly towards the front, and when the piston is at back dead center, the valve needs to be displaced slightly toward the rear. This suggests that we can add a mechanical connection from the valve stem to the main crosshead and get the lap and lead from there. So let's center the radius rod to place the valve in the middle of its travel. Now we add this second mechanical connection by first disconnecting the radius rod from the valve stem. Next, we hang a lever plumb vertical from the radius rod and pin it to the valve crosshead when the valve is centered in its seat. The connection point to the valve crosshead is very close to the top of the lever, which means the valve will not move much when the bottom of the lever is yanked back and forth. But that is exactly the point. We are talking about providing lap and lead here, and the lap plus the lead is only 1 7/8 inches. The bottom of the lever will be connected to the main crosshead, so it will copy the piston's motion. But before we make this link, we need to roll the locomotive slightly so the piston is exactly at the center of its stroke. Now we link the lever up with the crosshead by inserting the union link. Because the lever is plumb vertical when the piston is at the center of its stroke, the lever will displace the valve by equal amounts forward and backward when the piston reaches the front or back of its stroke. And the amount by which the valve is displaced will be determined by the length of the lever and its connection points, which must be carefully chosen to provide the correct lap and lead. If we take the piston to the back of its stroke, the bottom of the lever moves a distance of 17 inches, which is half the 34-inch stroke of this locomotive. The valve will be displaced in the same direction, toward the back, and because we have similar triangles here, the valve's displacement will be proportional to the lengths of the lever segments. By designing the lever properly with the distance between the connection points just right, we can ensure that the 17-inch displacement down here gives a valve displacement of 1 7/8 inches, which is the lap plus the lead. Notice that the valve has now moved sufficiently to open the rear ports to the steam chest for admission of steam, as must be the case when the lap is cleared and the valve has been given lead. If we now proceed to move the locomotive until the piston is at the front, the bottom of the lever is now 17 inches in front of the mid-stroke position, and the combination lever has now moved the valve 1 7/8 inches forward of the center position, which clears the lap and provides lead at the front admission port. In these views, we have kept the gear centered, which results in the valve getting no motion from the eccentric crank and the gear link. All the motion here is being provided by the main crosshead, geared down by the combination lever, so the valve is moving less than 4 inches from end to end, perfectly in phase with the piston. An engine that has been hooked up like this to completely cut out the eccentric motion from the valve would never see valves open more than the 3/16 inches of lead they have been given, and they close at something like 15 or 20% cutoff, which makes for very limited operation. This brings us back to the need to adjust the valve travel and control the amount of motion provided by the radius rod up here at the top of the combination lever. But first, while we are looking at how the combination lever is set up, I should mention that you might occasionally see a locomotive whose radius rod is connected to the combination lever below the valve stem, like this. This is a dead giveaway that the locomotive has outside admission valves. When the crosshead pulls the bottom of the combination lever to one end, the valve will be displaced in the opposite direction, which is necessary to provide the lap and lead for admission of steam over the outside edges of the ports. On these locomotives with outside admission valves, you will usually also see the eccentric crank angled in the opposite direction so that it leads rather than follows the main crank pin by a quarter turn. This is done because outside admission valves must be a half stroke ahead of the piston rather than a half stroke behind. You might also see the eccentric crank in this strange-looking orientation on some locomotives with inside admission valves. In this case, the eccentric crank's leading angle indicates that the valve gear is set up for indirect motion, meaning that, to run the engine in the forward direction, the radius rod is raised up to the upper section of the gear link like this, instead of being dropped below the trunnion. The radius rod will now be pushed forward when the eccentric rod pulls back on the link, and vice versa, hence the term indirect. This reversal of the radius rod's motion is canceled out by the eccentric crank having been moved across the wheel, so the end result is the same as in the direct motion valve gear we have been building up. We can see that the valve is open to admit steam to the front side of the cylinder, confirming that the engine will run forward. And to put an indirect motion valve gear into reverse, the radius rod is dropped down to the lower half of the link like this. This now moves the valve so that it will admit steam to the backside of the cylinder upon starting, which for this wheel position will cause the engine to run in reverse. Relatively few locomotives are set up with indirect motion valve gear, and there are at least two very good reasons for this, as we will see. Now back to the direct motion valve gear we have been developing. We saw earlier how the valve travel can be changed by adjusting the radius rod's connection point on the gear link, and this is a good time to reintroduce valve motion rule number 3. Shortening the length of the valve's travel causes cutoff to occur earlier in the piston's stroke. Adjusting the steam cutoff is the reason why we want the ability to change the valve's travel, and to implement this rule, there is one final addition we need to make to our valve gear mechanism. We need a linkage to accomplish this adjustment of the radius rod's hookup point. To do this, we will extend the radius rod out behind the gear link and hang this end of the radius rod from a bar called the radius rod hanger that is suspended from an adjustment linkage operated by the locomotive's power reverse. There are several different forms that this radius rod hanger and the associated linkage can take, but they all perform the same function. And when the engineer adjusts the engine's reverse setting, the radius rod is raised or lowered to place its connection at a different point on the curved gear link. And with the addition of this radius rod hanger and adjustment mechanism, we now have the complete, fully developed Walschaerts valve gear mechanism. Let's move the reverse lever to put the engine in full forward gear and watch the engine run. In full gear, the eccentric crank is imparting maximum travel to the valve through the curved link, and the radius rod is reciprocating through a range of about 8 inches. This motion is applied to the top of the combination lever, and it is combined with the motion imparted to the lever's other end to produce the final valve motion at the valve's connection point. Because the two ends of the combination lever are being driven 90 degrees out of phase, these two contributions to the valve motion do not cancel each other out, but modify each other at different points in the stroke to produce the motion we want. In this example, with the engine in full gear, most of the valve's motion is given by the radius rod, and the main crosshead's contribution through the combination lever is making a small correction to provide the lap and lead. As the piston reaches the end of its stroke, The combination lever is now modifying the valve's position to pull it 1 7/8 inches backward from the location the valve would otherwise have had, and this provides the lap and lead that the valve must be given to begin the next stroke. At stroke end, the valve is open to admission by 3/16 of an inch, which is the amount of lead given to this locomotive. As the piston stroke begins, the radius rod continues to pull the valve toward the back, opening the port wider for admission of steam from the steam chest. Moving along in the piston stroke, the valve eventually reverses direction and starts to close when the forward speed of the combination lever overtakes the rearward speed of the radius rod. When the valve closes off the admission edge of the port from the steam chest, we have cutoff. And notice that both the radius rod and the combination lever are pulling the valve forward now. This means that the valve is moving at high speed and cutoff happens lightning fast, exactly the kind of precise valve event we want. Finally, as the piston approaches the end of its stroke, the exhaust edge of the port opens to the exhaust chamber and the release event occurs. Again at this event, both the radius rod and the combination lever are still pulling the valve forward, so the release event should happen quickly and produce a nice sharp crack from the stack. Very soon, shortly before the piston reaches the front end of its stroke, the front ports open to admission. At stroke end, the combination lever has now displaced the valve 1 7/8 inches forward of the position where the radius rod alone would have placed it, the center, and this has cleared the lap and provided the lead to the front port. The piston now begins its rearward stroke, and the sequence of valve events proceeds for the front side of the cylinder. Now at the back of the cylinder, let's stop and observe the positions of the valve gear and combination lever. The piston, and therefore the combination lever, are at their furthest back positions, so the combination lever has provided lap and lead to the valve. The eccentric crank and gear link are in their neutral positions, completely centered. If we change the gear setting here, the valve does not move at all. The link's center of curvature now coincides with the radius rod's pivot point, and for any cutoff setting, the valve will always be in the exact same position, opened by the amount of lead it has been given here. This illustrates that the Walschaerts valve gear is a constant lead valve gear. The lead remains the same for all cutoff settings. This feature is typically regarded as a major advantage of Walschaerts over earlier valve gears whose lead would vary as the cutoff setting was changed. To study the valve gear's motion in more detail, let's focus on the radius rod hanger. The radius rod's tail end is constrained to swing in an arc centered on the hanger's pivot point. The radius rod is driven along this arc by the link block, which traces a similar arc path over here. The link block is carried within the channel in the curved link, which cannot follow the same curved path because it has its own pivot point here that forces its walls touching the link block to move along this path. The mismatch between these curved paths results in the link block sliding against the edges of the link's curved channel as it goes through its motion. One common misconception about Walschaerts valve gear and the link motion is the assumption that the link block only slips when the cutoff setting is being adjusted. In reality, the link block is never fixed to the link and always experiences some sliding, even during normal operation of the engine. To see this, let's get a close-up view of the link. If we cut away part of the outer cover plate, we can get a clear view of the link block seated against its channel within the link. Let's make a small mark on the link, even with the edge of the link block. As the engine runs, we can see a slight movement of the link block relative to this fixed mark, and this shows that the link block is experiencing a small amount of sliding along the inner surface of the link channel. Let's now hook the gear up to shorten the cutoff setting. We see the radius rod hanger pull the radius rod upward, so the link block moved closer to the link's pivot point, or trunnion. This will cause the link block to be carried through a shorter arc path as compared to its path in full gear, and this will shorten the valve travel. We can see now that the valve travel has been shortened. Instead of moving through the full 8-inch travel like this, the valve is now confined to this smaller range of travel, about 7 inches here. This is happening because the radius rod is moving through a narrower range, and this has two important consequences. First, because the valve never travels to these far regions out here, it does not open the admission ports as wide. Here we can see that the ports are never completely open to admission before the valve reverses direction and begins to close. A second consequence of the reduced radius rod travel is that the combination lever's motion overtakes the radius rod's motion earlier in the stroke, and this results in cutoff occurring earlier. The radius rod is moving through a shorter distance during each cycle, and this means that its linear speed is lower than it was at full travel. Notice how the valve reverses direction and begins to close while the radius rod is still moving backward. The shorter travel and earlier reversal combine to make cutoff, and indeed all the valve events, happen earlier in the piston stroke. Let's now hook up the reverse lever to give an even shorter cutoff setting. Here, the radius rod's travel has been cut way down because the link block has been drawn up nearly to the center of the link. In fact, the radius rod is now providing less travel to the valve than the combination lever, which always provides 3 3/4 inches, twice the lap in the lead, of motion at the valve stem. This means that the valve travel can never be less than 3 3/4 inches. Even if the reverser were centered and the radius rod were not moving at all, the combination lever would still be moving the valve by this amount. At short cutoff settings like this, the valve travel is just barely greater than the 3 3/4 inches minimum. Most of the valve's motion is coming from the combination lever now, and the valve is moving nearly in phase with the piston. The small amount of motion being provided by the radius rod is acting to delay reversal of the valve's motion only slightly behind the combination lever's motion, and all the valve events are delayed only slightly behind the time when they would occur if the combination lever were acting alone. As the piston begins its stroke, the valve opens only a little bit beyond the lead before it reverses direction and begins to close. The radius rod doesn't provide very much displacement, and its slow speed allows the combination lever to quickly overtake it and reverse the valve. Cutoff occurs early, about 30 or 40% into the piston stroke. Comparing this to the frame we saw earlier with the piston in the same position but the valve set for full travel, we see that the radius rod was further forward, which placed the valve significantly further forward in the valve chamber where it was still open to admission and not yet beginning to close. With the gear hooked up, the valve is now reaching cutoff at this point in the piston stroke. Then release happens earlier, which wastes some of the benefit of the earlier cutoff, but it also allows more time for the steam to exit the cylinder. This is very useful to allow the cylinder to breathe better at high speeds when these short cutoff settings are typically used. Again, comparing to the same crank position earlier in full gear, the valve was just about reaching cutoff. At maximum cutoff, the radius rod was also pulling back on the valve at higher speed here because it was being driven through a longer arc by a point further out from the link trunnion. This higher speed will pull the valve across the ports faster and provide a shorter period for steam expansion in the cylinder. By contrast, here in short gear, the radius rod's shorter range of motion leaves it moving with less speed, which has allowed the valve more time to dwell over the ports and given the steam more time for expansion in the cylinder. At the other end of the cylinder, we have an earlier closure of the exhaust port, and pre-admission begins slightly earlier. While the amount of lead, as seen at the beginning of each stroke, is always constant with this valve gear, the timing when the valve opens to the steam chest will vary. Notice how the motion just looks different than we saw earlier when the engine was in full gear. Instead of being out of step with the piston, the valve is now moving almost together with the piston, with the radius rod's short travel delaying each valve event only a little. Now we'll put the engine in reverse and watch the valve motion. To reverse the engine, the radius rod needs to be shifted to the other end of the link. As we saw earlier, this will cause the radius rod to drive the valve in the opposite direction. The valve has moved, so it is now opening the backside of the cylinder to the steam chest. So when we open the throttle to supply steam, the engine will start moving in reverse. As we start the engine and the piston moves toward the front, when we reach front dead center, the valve is opened by the constant 3/16 inch lead to begin the next stroke. As the piston begins its stroke, the radius rod is rapidly pushing the valve forward to open it further to admission. And it does open wide because we are in full reverse gear here. Eventually the valve reverses direction and begins to close, and both the radius rod and combination lever are pulling in the same direction now to bring the valve to cutoff. As we saw earlier, when the radius rod and combination lever are both pulling together in the same direction, the valve's speed is higher, resulting in a sharp cutoff and a sharp release near the end of the stroke. The sequence of valve events is the same as we saw in forward motion, as it must be for a properly running engine. By shifting the gear into reverse, we move the radius rod across the link trunnion to move in the opposite direction, which is equivalent to driving the radius rod from a point diametrically across the wheel. This would give motion that is a quarter turn ahead of, rather than a quarter turn behind, the main crank pin, except that the wheel is now turning in the other direction. The reverse rotation cancels out the rod's shift across the link trunnion, and the end result is that the radius rod's motion is still a quarter turn behind the main crank pin. The relationship between the radius rod's motion and the combination lever's motion at various points in the stroke is the same as in forward motion, and this produces the same valve motion we saw before. Reversing the engine really is as simple as moving the valve's drive point across the wheel to redefine what direction the engine sees as forward. As we watch the engine run in reverse, we can see that the slip of the link block within the link is very noticeable here. The radius rod is now swinging from a point that has been moved up here, and this means that it and the link block follow curved paths like this. The link block would need to follow this path to copy the motion of the link and experience no slip against the walls of the link. The difference between these two paths is much more drastic than we saw in forward gear, and this means more relative motion between them. This is one big reason why it is preferable to set up Walschaerts valve gear for direct motion, with forward motion driving the valve from the lower half of the link. Because locomotives typically spend most of their time operating in forward gear, we want to take advantage of the lower mechanical wear and more precise motion given by the bottom half of the link. The second big reason why we prefer to drive the valve from the lower half of the link in forward gear is seen if we consider what happens if the radius rod hanger snaps during operation. If the hanger fails, the radius rod will fall under its own weight to the bottom of the link. A sudden shift like this would place high stress on the running gear, particularly if it happens at high speed. If the radius rod hanger broke on an engine that is set up for indirect valve motion, the engine would suddenly be shifted into reverse while traveling forward at high speed, and this would likely destroy the running gear. Because high speeds are far more likely to be used when the engine is running forward, it is better to have the bottom of the link give forward motion than reverse motion. This way, if a hanger failure results in a reversal of the engine, it would be a shift from reverse into forward gear, and this would most likely happen at slow speed. We have seen how the three rules of valve motion can show us the way to a mechanism that drives the valve with a motion that satisfies the requirements for a properly running engine. In this journey, we have followed the step-by-step development of the Walschaerts valve gear arrangement. We have examined geometric features of the running gear that affect the valve gear's operation and need to be addressed. And we have looked at the nature of the valve motion provided by the valve gear and how it changes as the cutoff setting is changed. I hope these illustrations have helped to make the Walschaerts valve gear easier to understand, and I hope you'll join me for the next video, which will look at Baker valve gear.